balance between what you're going to save on the motor and how much money you could potentially add on the electronics. Because people sometimes they're saving a lot. They're removing magnets, rare earth magnet on the motor, so the motor is cheaper, but they need more current on the inverter, so the inverter is more expensive. So finally, when you combine the two, they're not cheaper.
Hi everyone, I'm Yu-Chi. Today we are going to talk about the YEESMA's technical breakthrough in the motor industry. And really happy to see you again, Philippe.
Happy to see you again as well, Yu-Chi.
And then most of our audience are engineers and also like a product developer who are really interested in the technology. So I would like to ask you to break down this for us. Like what's a core innovation that YEESMA is offering to the industry?
Okay, I'll try to be short because I can talk about YEESMA technology for hours. YEESMA is really, in essence, first of all, it's an electrically excited synchronous machine. And it's a combination actually of an axial flux, so we're using an axial flux topology versus a radial flux, which is commonly used nowadays. And the second combination we use is it's an axial flux, electrically excited synchronous machine. So that's really the whole core things. And because we are marrying those two technologies, it's an electrically excited, there's no magnets, and it's an axial flux, it gives much more powerful solution than typical radial flux. So that's really the whole marriage between an axial flux and an EESM. That's why YEESMA. That's the core technology of YEESMA.
You're using the YEESMA which replaces like a permanent magnet with the copper field windings, right? And what's the advantage of this approach to improve like a thermal control or long-term operations?
Okay, by the way, let me correct one thing. We can use aluminum as well. We cannot only use copper, we can use copper or aluminum. In terms, just trying to respond to your question in terms of thermal or continuous operation, because it's an axial flux, we can better cool it actually, because all our coils are completely exposed, so we can easily put some oil cooling, for example, and the oil will go directly on the wine. So it's a machine which can naturally be better cooled than a radial flux. Radial flux, typically, when you have an inner rotor, the oil has difficulties to access to those coils. Because it's an axial flux with rotor windings, those rotor windings completely exposed to a good cooling. If you have a good cooling, you can have lower temperature, you can have higher continuous power. So that's all I do.
Does it make the manufacturing more difficult because without the precise magnet alignment, it seems like it could be a double-edged sword?
Actually, it's the other way around. When you have a permanent magnet, you have a huge attraction force. You know, when you have a magnet likes to attract any steel or another magnet. In our case, we have electromagnets. And when we are assembling, there's no power supply, nothing is supplied. So those magnets, those electromagnets, are inert. I mean, they don't exist actually. So during the assembly, it's actually much easier because we don't have any attraction force. And that's really one of the key things in terms of manufacturing, of assembly. When you don't have that attraction force, it's making the whole thing much easier than typical axial flux with permanent magnets.
I would like to have another addition question. It's like, in the beginning, how you come up with this idea?
How did we have this? To be honest, we started first with radial flux. We've been working on radial flux on radial flux EESM. I think I've been working this even during my PhD. I had a radial flux as well, EESM. And the more we were working on that, the more the whole thinking was, okay, if you could have a radial flux EESM where we can really cool it, we would have a fantastic machine, which would be even more compact than an IPM, electric motor with permanent magnets. So that's really how the whole idea came in. And recently, more and more people are talking about axial flux with permanent magnets. Let's be very honest, this is the most compact machine you can find. YEESMA is not saying we're going to be smarter than axial flux PM. You have to be very transparent and honest. Axial flux PM is going to be the most compact. But if you have an axial flux and an EESM, this is really where you have the right balance. You are not the most compact, but you're already super compact compared to radial flux. And cost-wise, you really have still the same feature, and you're even cheaper than a radial flux EESM, because an axial flux EESM can be more compact. More compact, less material, cheaper.
And what kind of feedback is currently you receive from your clients like OEMs or tier ones?
We have extremely good feedback. It's definitely a new technology. People are asking, it's very strange technology to be honest, because nobody really did that. So we really have very good, strong attention. It's a very, people didn't believe us when we really came up with those numbers, you know, when we say 30, 40%, people saying you can't have 30, 40% in automotive, that doesn't work. But the more we work, the more we even build a prototype and showing that our numbers are really correct, people are starting believing us. I'm not saying they didn't believe us at all, but it was, to be honest, too good to be true. But numbers are really coming along, so that's coming now.
Do you invite any institutes or like academic lab to test it together?
Yes, we are working now, I can quote their name actually, 𝗬𝗵𝘁𝗀𝗍 in Modena, in Italy, which is working with us actually. So they help us actually assembling, and they help us now testing as an external partner and testing our parts, checking that what we were predicting is correct to what we're measuring on a test bench.
That sounds amazing.
A lot of people are talking about Wave 3. A lot of guys are coming with new technologies, but then they are big. Nobody's talking about that. They are much bigger than us, packaging.
Yeah.
They are more expensive on the electronic side, so they're saving a lot on the machine, but they're ignoring the inverter. The electronic is more expensive.
Yeah.
When you add those two, it's more expensive.
Let's see.
So that's really one thing I'd like to really, if you ask me the question, I could say, hey, people are talking, if you could allow me to talk about that, I would be good.
Of course. But in general, is it possible to keep the balance between the removing the permanent magnet and also keep the low cost?
That's a very good question, and actually, thank you for offering me. You can see, and many competitors, I can mention a couple of technologies, but let me mention one that a lot of people are talking about. It's called synchronous reluctance. And this technology definitely helps you reducing the rare earth magnets, but there's a but actually. This technology actually, for same torque and power ratings, you need to be at least 30 to 40% bigger. So you have a packaging penalty with this technology. And there's another but. You're gonna save on the machine, on the motor side, so you will have definitely less rare earth. You're gonna be cheaper on the motor side, even if you have 30 to 40% bigger. The other but is you have to invest money on the inverter side, because the inverter requires higher phase current to reach the same power. We don't have that issue with YEESMA in an EESM. YEESMA as an axial flux EESM, the machine is much more compact, and we need less phase current. So the inverter is also cheaper. So not only we have a cheaper motor, but we also have a cheaper inverter. When you combine the two, that's how we came up with big numbers in terms of bill of material reduction. It's not only the motor, it's also the inverter. That's why we have a double-digit production. And we are smaller, we are not bigger like a synchronous motor.
But currently, did you meet any a challenge or limitation of the YEESMA's technology?
Yes, we do have limitations. YEESMA core technology is an axial flux EESM, and an axial flux, by definition, it's a big diameter. Big diameters machines don't like high speed. So that's the challenge, how to reach high speeds. And the trend nowadays is more and more higher and higher speed, so that's really a challenge. If you want to address the high speed applications, that's where we're going to have a challenge. But we do have some ideas actually to meet this challenge. I can't talk about that. It's still something we're working on, heavily working on, but that's definitely a challenge, like any axial flux going high speed.
So from the technology perspective, what is the next for YEESMA to the next stage in terms of R&D?
Okay, in terms of R&D, so far, quite honestly, we first focus on the electric motor itself. But the more we're working on it, the more we see that we can even extend and actually increase the advantages of YEESMA more on the electronic side actually as well. This is something we knew it would be some advantages, but we're really discovering that we really have much actually better savings on the electronics as well, because specifically in our structure where we have two rotors, we have two big electromagnets, we can cool them, we can put a lot of current in what we call the rotor excitation. When you have a lot of high excitation in an EESM, that helps actually reducing the phase current you need in the stator. Reducing those phase currents has a huge impact on the electronics on the inverter side. So our future step in terms of R&D is definitely working on the motor, but really looking on the impact on the inverter as well, and really giving value to that as well. Because we're not saving money only in the motor, but we're also saving in the inverter as well.
we are really looking forward to the next set of YEESMA's R&D. And yeah, the YEESMA's technology just not make the motors have to keep like a balance between the cost and also the efficiency, but it's not like a compromise anymore. So thank you again for these amazing interviews, and we will see you guys next time.
Thank you for the opportunity.
Yeah, okay.
Thank you, Yuchi.